microeconomics, or in this course, we are going to study what may be called classical microeconomics. And it's the study of markets and the price system. And the fundamental question is, how do the various economic actors in a market make their decisions? We'll model that. And then how do those decisions interact to produce a market outcome in terms of quantity produced and the price that is obtained, and how it affects the welfare, well-being of the various market participants, namely the buyers and the sellers. In this classical approach, the one standard assumption is the assumption of perfect competition. So that's what we will start with. Perfect competition, broadly speaking, is a situation or a market where there's a very large number of buyers and sellers, so that each individual buyer or seller is insignificant. If an individual buyer or seller changes her decisions, supplies a little more or buys a little less, that's going to be a drop in the ocean, and therefore is not going to affect the market prices significantly. Yes, that's the assumption of the perfect competition model. As a result, in perfect competition, we model economic agents as engaging in price-taking behavior, right? So I go to the market to buy some rice. I assume that whatever the market price was of rice before I hit the market is not going to change just because I buy 2 extra kgs, right? That's going to leave no impact on prices. So price-taking behavior is the key. And then, of course, we'll move on to other market structures where some buyer or some seller may have significant market power, but let's not jump the gun, right? We'll start with perfect competition. Now, in the traditional, sort of the usual approach, we first start from the individual, okay? We study household decision-making or individual decision-making. An individual goes and buys various things from the market, right? Food items, clothing items, housing, and so on. And we study what is the basis of this sort of choice, what determines how much of every good a consumer will demand or want to buy. And then we turn our focus on the study of the firm, which is the source of supply of goods and services, right? Various things like computers and food and so on. And then we bring it all together and do an analysis of market clearing prices, equilibrium, and so on. Now, I'm going to change the sequence a little bit. I'll postpone a detailed study of household choices and firms' decision-making, right? That'll come as topics 2 and 3. In topic 1, I will jump right into developing some understanding of the price system itself. So I'll start at the theory of prices. And in doing so, I'll keep the consumer's side and the firm's side, their behavior, I'll keep it somewhat less than general, right? We'll not do a general analysis. I'll assume special functional forms and so on. Because I think that's a better approach, right? So we'll dig into the individual choice in more detail later. Okay, so let's start with a very simple model of the market for a certain good, let's say bread, all right? So we have the market for bread, and there are a finite number of consumers who want to buy bread, right? So they are indexed by I, so I goes from 1 to n. So now, each consumer I, has a utility function, and in this sort of very simple starting framework, we will assume that the utility function is a function of 2 things, 2 quantities. One is the quantity of the good in question, right? Bread, namely, that is QI. So this is consumer I's consumption of bread. And MI, which is the money spent on all other goods, right? So think of MI, sometimes it's called a composite commodity. It's everything else lumped together as an alternative good to spend on, right? So, of course, in reality, there are many, many different goods, and the kind of theory we're building is perfectly capable of handling many more goods and services, but this is a starting point. So we'll keep things simple and say what the consumer cares about is how much bread she consumes and how much money she spends on everything else, right? Other goods. Not only that, I'll simplify it further by assuming a particular form of this so-called utility function, right? And I'll assume that, first of all, it is additively separable, right? This function could have taken many different forms, but will take an additively separable form. So there's some utility from the bread that I have chosen to buy and eat, and some utility from the money I'm spending on other things, and it takes this additive form, we'll assume. Not only that, even more, we'll say the bread utility component is nonlinear, right? This captured by this U function, right? UI of QI, but the utility gain from consuming other stuff is linear, right? So it's just plus MI. I could have put a constant here, but I can, without loss of generality, take that constant to be 1. Both these quantities are continuous variables, we'll assume, for mathematical purposes. So whatever bread is, I can buy it in any arbitrary fraction. In fact, not even fraction, any real number, right? That's a useful sort of approximation. We can just apply calculus. That's why we want to make that assumption. Okay, now let's pause for a moment and think about what this utility function means. Before that, let's talk about what is the unit of measurement. All right, this U function and M function, they spit out some numbers. Those numbers are measured in what unit? Okay, and the unit is going to be money. Now, this is by definition money spent on everything else. So whatever this utility of bread that we are talking about is also measured in monetary terms in this framework that we are building right now. Now, what does that mean, right? So this function could spit out a value like, for example, if I buy 3 units of bread, that gives me a utility of 25 rupees, okay? What does that mean? One way to think about it is in terms of willingness to pay, right? So I walk into a store and there are shoes. I want to buy a pair of shoes, and there's a pair which I'm looking at. You could ask me, what's the maximum you want to pay for this pair of shoes? Now, assume for a moment that I am not being strategic, that I'm giving an honest answer. Of course, if the seller asks me the question, I want to maybe game the question and underreport my willingness to pay. But in my mind, there is some number, right? If I have taken a close look and have determined how much I like it. So I could, for example, pay up to 3,000 rupees for that pair of shoes that I'm looking at. So then you could say that, well, the utility to me of this pair of shoes is 3,000 rupees. Okay. Now, if there's another pair which I'm looking at, you could ask, oh, how much are you willing to pay for both these pairs, right? And maybe my true honest answer in my mind is 5,000 rupees. So then the utility for the second pair is 2,000, or that we may call that marginal utility, right? The extra utility I get if I buy a second pair starting from the first, my willingness to pay go up from 3,000 to 5,000. So that extra 2,000 is my marginal utility in monetary terms of the second pair of shoes. Okay, so this is called a money metric utility function. Everything is measured in terms of the currency, rupees, dollars, whatever, what have you. And its functional form is sometimes called quasi-linear, right? One component of utility, this coming from MI, is linear, the other is not, but they're additively separable. So this is a quasi-linear and money metric utility function that we are assuming for consumers. Now, we may want to impose some natural or plausible assumptions on the shape of this utility function for bread, for the good in question. What are natural assumptions? One natural assumption is that the first derivative is strictly positive, right? Which is basically saying the more the merrier. If I have more of something, holding everything else constant, that makes me better off as a consumer. I get more utility, or whatever you want to call that. This is in calculus terms, right? It means that the derivative of this function is strictly positive. This is, I presume all of you are familiar with this sort of notation, U prime, that is basically dui dqi, right? It's the derivative of this function. Now, we may also want to impose a sign on the second derivative, and we'll impose the negative sign. What does that mean? That means that as I get to consume more and more bread, of course, my utility goes up, or my willingness to pay goes up, right? But at a rate which is getting smaller and smaller, right? This is sometimes called the diminishing marginal utility assumption, that for the first loaf of bread, I'm willing to pay, let's say, 10 rupees. But for the second loaf, I will be willing to pay less than 10 rupees, maybe 8 rupees. For the third loaf, even less than that, maybe 5 rupees, and so on, right? That's an assumption we are going to make. Now, in reality, for a particular consumer, that assumption may or may not be true. All these assumptions that we make at the start of our economic models, they are assumptions, and they could empirically be false in principle. We try to choose our assumptions so that they have some relevance, so that they apply to the economic world, or to most people, most economic actors. But we also always have to be aware that, this is social science. So in science, we have to risk something. We have to risk formulating hypotheses or theories which are falsifiable, right? They could be false, and there has to be a way of looking at data and determining whether the theory matches with the data or not, right? So it is an assumption which empirically may or may not be true, but it appeals to us if we think of it introspectively. If I already have a lot of bread, I'm kind of satiated. An extra loaf is not that attractive to me. We'll also make sort of endpoint conditions. These are called in-order conditions sometimes. If the quantity is 0, then marginal utility is infinity. That means starting from 0, if I get just an extra morsel of bread, then in derivative terms, it gives me a lot of extra utility, right? Infinitely high. And if I'm consuming very large quantities of bread, then my marginal utility is approaching 0. These in-order conditions and so on, they guarantee interior solutions that the rational consumer will end up choosing some positive and finite amount, right? That's the purpose. Now, our consumer will have a budget constraint, right? And that's represented by this equation. On the left-hand side, we have the total spending of the consumer, right? If the market price for bread is P, then P times QI is the amount of money which she spends on bread. And this is the amount of money spent on everything else. So that has to match up to her income, right? In principle, she can spend less. So sometimes we may want to write this as a less than equal to, right? But if she likes all the goods, bread and other things, then she will use up all the resources she has. So in general, this holds with equality. YI is the monetary income of consumer I. Okay, now, having written down the sort of basic, the circumstances in which our consumer is going to make a choice, now we have to take a stance on what the consumer is about to do. How does she make decisions? And there comes the assumption of a rational consumer. right? In this sort of classical framework, we will assume that consumers are rational decision makers. Okay, so what does that mean? Let's pause for a moment and think about it, and let's be absolutely clear about what we mean by a rational actor in this sort of theoretical framework. In everyday use, sometimes by rational, we mean something like prudent or wise, right? So if I'm eating a lot of junk food, you might say I'm not being rational, right? I'm for temporary pleasures, I'm sacrificing my future health. We are not using the term in that sense, right? So if we look at someone and find that this person consumes a lot of junk food, does not save up for retirement, drives at a high speed, we're not going to say that these are prima facie irrational choices. We may say these are sort of rash choices, reckless choices, but not irrational choices. The sense in which the term rational choice is employed is the following. The consumer or the agent has some preferences. We are not going to question those preferences. We may want to make some assumptions about the structure of preferences, but preferences are whatever they are, right? Rational choice means the ability to fulfill your desires or climb up your preference ladder as much as you can, given the resources that you have, income, money, etc. And given your objectives or your preferences, you make the most of it. Okay, so if I'm somebody who values the taste of food, how much pleasure it gives me, and puts a lot of weight on that and less weight on my future health prospects 10 or 20 years down the line, whether my cholesterol is under control or not. If I have those preferences, then eating junk food is a rational choice for me, right? I can rationalize it saying that, okay, that's the way I like, that's the way I want to lead my life. And so I will just go for fast food because it tastes good instead of boiled vegetables. Yeah. So I hope I've made that point. Yes, that rational choice in our framework is basically some sort of maximizing behavior. You have certain structure preferences, certain utilities, and you maximize it. And if your choice ends up maximizing your own preferences, which we won't question, then we'll say you're a rational agent. Okay, so having said all of that, let's bring that into practice in this simple model. So the assumption of rationality then in this kind of classical approach boils down to modeling economic actors like consumers, households, firms as doing some sort of maximization exercise. Yes. And their choices, their behavior, and the responses to various economic stimuli will be understood or can be understood as how they adjust their maximization when the circumstances change, like some price goes up, some other price goes down, their incomes change, and so on. Right? So maximization or constrained maximization becomes the sort of engine of this sort of classical economic theory. Now we can formulate the agent's problem as this following maximization problem. Maximize the overall utility from consuming bread and other things, subject to not exceeding your budget given by this weak inequality. Right? Now, this is a constrained optimization problem, a single constraint, and it's an inequality constraint. But if you look at it, if the utility is increasing in both Q and M, then obviously the best choice will be such that no money is wasted, right? So this inequality, this constraint will bind, essentially. It'll be an equality constraint. So if I replace this inequality constraint by the corresponding equality constraint, I'll get the same answer. So I can do that, right? Now, the moment I do that, how do I solve this problem mathematically? Well, at this point, because the problem is very, very simple, I can do it by substitution. Essentially, what I'm going to do is, if you now think of this as an equation, mi is essentially yi minus p of qi, right? So I'll get rid of the constraint and replace mi by yi minus p qi, right? So that's what I've done in this slide. So I've converted the constrained optimization problem into an unconstrained optimization problem. All right. And there's a little, I shouldn't have, under maximization in the initial formulation, the choices were Q and M. Once I do the substitution, the choice really becomes Q, right? M has disappeared because of the substitution. So now this is a single variable unconstrained optimization problem. Now, this substitution trick, of course, won't work, and we'll have to use more powerful methods like Lagrangian, but we'll come there. For the moment, this is enough. All right. So as you know, if you solve a simple one variable maximization problem, maximize fx, okay? At what point does a function reach a peak? Right? In the simplest of cases, this should be, this is very basic calculus, but let me just, for the sake of completeness, just very quickly say, if I'm solving a problem like this, maximize a function by choosing x, and I'm looking for the magic value of x, which will give me the highest possible value of the function. Well, I'm looking for a peak of the function, right? So the function's graph looks like this. This is the point where it reaches a maximum. Let's call that x star. X star is the maximizing value. And what is the property at the peak? At the peak, if you draw the slope of the function, it should be flat, right? Which means f prime, or the derivative, should take a 0 value at the peak. Now, of course, there are caveats, right? If you look at lowest values, that also has the same property. When a function reaches a trough, there also its derivative is equal to 0. So maxima and minima both have this property, right? That the derivative there vanishes. And we can usually find the points where the function reaches maximum or minimum by applying this principle, right? But there's a critical difference between the maximum and the minimum. So to distinguish maxima and minima, we have to look at the second derivative, right? So over here, in the case of the maximum, the function, the slope goes from positive to 0 to negative. So the first derivative is decreasing. That means the second derivative is negative. And in the case of the trough, the minimum, second derivative is just the other way around. It's positive, right? So in the simplest of cases, single variable unconstrained maximization, this is the principle. Maxima minima can be found by setting first derivative equal to 0, and to identify which is it. Is it a peak or a trough? We have to look at second derivative. Now, of course, as we look at more complicated problems, we'll first of all have multivariate functions of not just one variable, and we'll have one or more constraints. We have to maximize with respect to constraints. And then sometimes we have what are called corner solutions. Anyway, I'll come to all of that later, right? So this is the sort of starting principle of optimization. So I just wanted to very quickly remind you of that. I'm pretty sure most of all, this is just familiar to you, but doesn't hurt repetition. Okay. Now, if you apply that principle here, maximization, then what is called the first order necessary condition, first derivative must be 0. That gives us this equation, right? And what is this equation telling us? The economic interpretation is that I, as a consumer, should keep buying bread till I hit a point where the marginal utility equals price. Right. So initially, as I start from zero and I'm looking at a first loaf or a second loaf, the marginal utility of that measured in money terms may be much higher than the price. But as I'm buying more and more loaves of bread, my marginal utility is coming down. At some point, it becomes equal to whatever the price of a bread is, let's say 20 rupees. And at that point, I should not buy any more, right? This sort of classical economics is full of these marginal conditions, right? Marginal this equals marginal that. So it should be sort of bread and butter to you as you study this subject. Okay. Now, this optimality condition, this condition of optimal choice, utility maximizing choice, implicit, it contains information that gives us the demand curve or the demand function, right? That information is contained in this equation. What is a demand function? Right? A demand function tells us what a consumer, how much a consumer will demand or want to buy at various prices, right? Various prices of that good, maybe other goods. So a demand function could be, in general, a function of many different things, but the most critical thing among them is the price of the good in question. So let's hold everything else fixed, the price of other commodities, the consumer's income, the consumer's tastes, and then there will be a relationship between price and quantity demanded, right? As the price changes, the consumer will adjust her demand. That relationship is called the demand curve or the demand function. Demand function is more general, it's the demand curve, right? So this is the source of demand curve. It's the first order optimality condition arising out of the consumer's utility maximization. Now, of course, as I just said, second order conditions are important, right? What is the guarantee that this equation gives us a quantity which is not utility maximizing, but maybe it's utility minimizing? So you have to make sure that it's indeed a maximum. And that means the second derivative of this expression has to be negative, right? That will guarantee maximum. And if you take the second derivative, right, Q here is just linear. So when you differentiate twice, all you have is U double prime. So that has to be negative, right? The second derivative of the utility function for bread. And that's an assumption we have already made, right? Diminishing marginal utility. So diminishing marginal utility guarantees the second order condition. If we have made that assumption, we don't have to guarantee whether at that specific value of quantity, second derivative is negative. It's negative everywhere. So, okay, here's a particular example. Suppose U is a log function, right? Some constant alpha I times log of Qi. Then if we apply this equation, right, this marginal utility is essentially alpha I by Qi, right? So alpha I by Qi will be set equal to the price. And then just by transferring terms, we can express Q, the quantity the consumer will want to buy, in this form. It's alpha I by P. And so there's a negative relationship in this particular case between demand and price. As price goes up, this particular consumer will want to buy less and less, and in inverse proportion. Right? If the function was different, we'll have a different kind of relationship. Now, principles textbooks, right? If you're taking your first economics course, first year in college, they usually start by claiming a law called the law of demand, which says that other things equal, if the price of a good rises, consumers buy less of it or demand less of it. There's a negative relationship between quantity demanded and price. That's asserted as a law which presumably holds for all markets. Is that true over here? Okay. Given the assumptions we have made, and particularly the diminishing marginal utility and so on, from that, does the law of demand follow as a logical consequence? Later, in much more complex problems, the same argumentative trick will apply. Okay, so look at this very, very closely. All right. Okay, now, how can I prove this claim that the law of diminishing marginal utility implies the law of demand? Here's how. This is the first order condition, right? The maximizing consumer will always choose quantity from this equation by using this equation, so to speak. And that gives rise to the demand function Qi as a function of P. This is a demand function, right? This is a function which is derived from this equation. Now, if I rewrite the equation, and inside this function, instead of any arbitrary quantity, if I put down, if I insert the demand function itself, the way it has been defined, then this equation becomes an identity. What's the difference between an equation and an identity? So if I write this is an equation or an identity. It will only be true if x equal to either 3 or 1. It won't be true for any other value. But if I write x minus 2 squared equals x squared, that's 4x plus 4, this is an identity, and I can use 3 because insert whatever value of x you wish, this relationship is always valid. Okay? Now, why does that matter? If I take an equation, can I equate the derivatives of the two sides?
Yes,
I can't, right?
Yes.
Just check. The derivative of this is 2x minus 2. The derivative of the other side is 0. Okay. Even at these values, at the solution values, let's say 3, if you put in 3 here, the value of the derivative of the left-hand side is something positive, and it doesn't match the derivative of the right-hand side. So you can't equate derivatives of the two sides of an equation. But in the case of the identity, the derivative is 2x minus 2 on the left-hand side, and on the right-hand side, it's 2x minus 4, and those two things are equal. An identity is true by definition. Its two sides are true no matter what value you put in. So therefore, every property of the two sides will match. Okay, now that's an important part of the reasoning. So now, going back to where we were, if I take that first order condition and insert as the argument of the function, the demand function itself, it becomes an identity. And now I can equate the derivatives of the two sides if I differentiate with respect to the price, both sides, right? So that's what I've done. Chain rule. If I differentiate the left-hand side, you will have the second derivative of the utility function and then the derivative of what's inside. That's the chain rule of differentiation. So the derivative of what's inside is the slope of the demand function. So this product equals derivative of right-hand side, which is 1. And now by sort of pulling this thing down over here, we get slope of the demand function is equal to the reciprocal of the second derivative of the utility function. And now we can see the connection that I just claimed, right? Law of diminishing marginal utility tells us that this second derivative is negative, which means the slope of the demand curve itself will also be negative. So that's a proof that law of diminishing marginal utility implies the law of demand. Now, we have only shown this for the quasi-linear utility that we are considering. Okay. You may ask the question more generally, if the utility function doesn't take this specific form, will the law of demand always be true? And the answer to that is no, not necessarily, but we'll see that when we study consumer theory in more detail. Intuitively, it seems that, it has to be true. You may be sort of, if you just casually introspect or look around, you might think, hey, if something becomes more expensive, why will people buy more of it? There are subtle reasons why they might, but we don't see that in the quasi-linear utility case. So at this point, we are not going to worry about that. We'll accept the law of demand as something valid and proceed with. Now, the last thing I want to talk about before ending today's lecture is consumer surplus. Unlike in the natural sciences, if you're an astrophysicist, you worry about, the law of the movement of planets. How will the planets behave? In economics, we are talking of how will human actors behave. But ultimately, we are interested in welfare, right? So if in a certain market, what will be the welfare of buyers and sellers? If conditions change, if some new tax is imposed, what will happen to the welfare of the various parties involved, right? Will it go down, go up, by how much, etc.? So a measure of welfare is very, very critical, and we want a precise and workable measure. So in this case, we can work with something called the consumer surplus. And what is consumer surplus? Consumer surplus here is the utility, the extra utility the consumer gets from having the opportunity to participate in this market, the market for bread, let's say. So we look at how much utility the consumer will get by this utility function if the market is there, and look at how much utility he'll get if the market wasn't there for some reason, right? The market didn't exist and he was not able to buy bread. And that difference is how much the consumer gains from having access to the market. So we can define that as the consumer surplus in this market. All right. So by that definition, participating in the market gives this, right? And if the market wasn't there, then everything will have to be spent on other goods. So the utility from bread would be zero. Let's normalize it to zero, right? And so MI, the money spent on other goods, will be the total income, YI. So that will be the utility. So if I take the difference, and that cancels out YI, and the difference is just this. So that difference is a measure of how much extra utility or happiness the market is providing this consumer, right? Of course, this incorporates the consumer's own voluntary optimal choice, okay? And that's because I've used the demand function in this. Now, one way to write it down is this, right? We know that differentiation and integration are opposite operations, okay? So if I take the derivative of this function, right, with respect to q, so that's this, okay, and then if I integrate it again, then I should get the same expression. So in other words, this line and this line are the same. This is the derivative of this function integrated from 0 to the relevant point, which is the point of purchase, right? So if I differentiate and then integrate again, I get back what I had to begin with, which explains this equality. All right. Now, once you look at this last line, there's a nice diagrammatic way to understand it. And that's on the next page, the next slide. In this quasi-linear utility framework, the marginal utility curve and the demand curve are one and the same, right? Why is that? That's very easy to see.
So because of the utility function, form of the utility function.
Let me explain that, then you can ask your question. Just hold on. So this is the marginal utility curve, right? Let's start with that. We know the optimizing principle says that for any price, take any price given by the market, say this price, the optimal choice comes from the rule price and marginal utility are the same. So at this price P, the optimum choice is QP given by this point of intersection. Now, this is true for every possible P that you might think of, right? P1, P2, P3. Now, what is a demand curve? A demand curve gives us, for every price, what is the quantity the consumer will buy. And so essentially, once we draw the marginal utility curve, it gives exactly that information, given the optimization principle. So the marginal utility curve is the demand curve of the consumer, right? Okay, now going back to this measure of welfare that we were trying to develop, what does it say? It says that welfare is the gap between marginal utility and price running from 0 to the quantity that the consumer actually buys. Okay. Now, if you come at the picture, this line, it doesn't have to be a line. This is marginal utility curve as well as demand curve, right? There's quantity on this axis. So that formula in the previous page is telling us we should really look at the gap between the marginal utility curve or the demand curve and the price line up to the quantity that the consumer buys. And that means this area, the area included under the demand curve and above the price line up to the relevant point. This is what is called consumer surplus. And what it really captures is what I said. It's the difference in utility between getting to participate in the market and choosing rationally, optimally, utility maximizing way, and not getting to participate in the market. It's a true measure of that, right? So that's something you need to remember, that this area is what is called consumer surplus. In this framework, it's measured in monetary terms, and it really captures what's the extra gain from